Welcome everybody. So welcome to today's session on boundary layer theory. So very good afternoon. So in this 45 minutes lecture, we are going to cover certain aspects of the boundary layer theory, just historical perspective, what was the idea that provoked the development of the boundary layer theory growth over a flat plate, the similarity solution, what is the Blassier solution, similarity solution, what is order of magnitude analysis, and other things will gradually go and cover in this session, right? Let's come to the boundary layer theory. It's in the year 1904. There was a German who is almost about 29 years old. In the Third International Mathematical Congress in Heidelberg, he came with a revolutionary idea of boundary layer theory, right? So unfortunately, at that point of time, that idea failed to catch the attention of most of the contemporary researchers across the world. Okay, almost Navier and Stokes did the full derivation of the Navier-Stokes equation around the mid of the 19th century, right? So almost another 5 decades of time, there was not any solution available, closed form of solution available to Navier-Stokes equation. Even if today's date, there is no any analytical solution available for the Navier-Stokes equation. So in the beginning of 19th, 20th century, what will happen? Wright brother invented the aeroplane. To design the aeroplane, lot of calculation required for fluid and hydrodynamic drag, lift, and other things, which essentially requires the solution of Navier-Stokes equation. But unfortunately, that time there is no supercomputer, no CFD, no numerical method, nothing was available. Even if the Navier-Stokes equation, direct form of Navier-Stokes equation solution is not available. Even if today's date, the analytical solution of Navier-Stokes equation is not available, and it's $1 million question by Clay Mathematical Institute. So in his 8-page long paper, he bring the revolution in the classical hydrodynamics, Prandtl, okay, and started the foundation of modern fluid mechanics. To understand what exactly this 8-page paper he did, let's go to the picture. The picture represents thing much more clarity. You can see it's a boat, okay, it's moving in some lake. So what will happen? So you can see the disturbance that is generated because of the movement of the boat that propagates towards some finite area, right, or some finite, up to some finite space in the lake, that is get affected by the disturbance, while the rest of the lake, they remains undisturbed. This is how what the boundary layer theory is exactly telling. If the boat is moving and the water is standstill, or the boat is standstill and the water is moving across the boat, they are almost similar situation. What this boundary layer theory is telling? The boundary layer theory is telling whenever there is a flow across a solid surface, okay, what will happen? By virtue of the no slip boundary condition, the fluid adjacent to the solid surface at rest. If far away from the solid surface, the fluid will move with a uniform velocity, right? Because there is not any solid surface to obstruct the flow. In between, the fluid get decelerated up to certain fraction of area where the effect of the presence of solid surface will be felt. Okay, that position where the effect of the presence of solid surface is felt, they named it as boundary layer. We'll come to formal definition gradually. Okay, so who is the messenger over here? The solid surface is giving some disturbances that is propagating to the fluid, right? So who is the messenger over here? The messenger over here is the viscosity. It is the property of the fluid. By virtue of this property, any disturbances that is creating in the fluid, that is propagating towards the solid surface. Let's come directly towards the picture to see what exactly the boundary layer. Okay, let's see. This is a simple picture. Hope all of you might have gone through it earlier. So what will happen? A uniform stream of fluid is coming, that is showing in the orange color at the here, with some velocity u infinity, right? when the uniform stream of fluid is coming, this is my flat plate which is at rest condition, right? So this uniform stream of fluid, while it is coming, it directly hits the start plate over here. We can tell it x0 position. Then what will happen? Once it hits the plate, so what will happen? The fluid which is adjacent to the solid plate, they will be at zero velocity because of the no slip boundary condition. The solid will not allow any tangential velocity to be growth just adjacent to the surface. So the fluid which is just adjacent to the surface, which is at zero velocity. Gradually what will happen? That layer will restrict the motion of the next layer of fluid. The next layer will restrict the subsequent. Gradually up to certain distance, the fluid motion will be restricted, right? So after that, again after a certain layer, again what will happen? The fluid motion will be undisturbed, means the fluid will pass through the same velocity u infinity, right? So now the broad picture we can divide into several zones. Okay, first the zone where the fluid motion is get affected by the presence of the solid layer, right? That zone we call as boundary layer zone, right? So then there is a zone where the fluid has a uniform velocity as it is. We call it as a core or the outer layer, right? In the boundary layer there is a edge, right? It's a two-dimensional view. There is a edge which is demarcating the boundary layer to the outer layer. That edge will call the boundary layer edge, right? So what will happen? So gradually, if you see the other thing we call the distance from the solid plate to the boundary layer edge, right? That keeps on increasing with respect to the length of the plate. Suppose my length of the plate is in x coordinate system, right? So if you go on moving in the x coordinate system, you can see the boundary layer edge, sorry, the thickness of the boundary layer. That is this blue line shows my thickness of the boundary layer, the distance between my plate to the edge of the boundary layer, that goes on increasing in the downstream direction, in the x direction, right? So then what is saying, my boundary layer thickness is keeps on increasing. This is here, my boundary layer thickness is this much. If you come to a little bit distance, the boundary layer thickness will go on increasing. Like that, theoretically, if you go on increasing the length of the plate, the boundary layer thickness keeps on increasing. But in reality, that is not the case, because what will happen? After certain point of time, there is a laminar boundary layer become transition. Then this is called the transition layer, and beyond the transition layer, the flow is turbulent, and there is a monotonic restriction on the growth of the boundary layer edge. So in this presentation, as it is a preliminary series on boundary layer theory, we'll keep our discussion restricted to within the laminar zone. That is the zone from here to here where we have a monotonic growth of boundary layer. So we'll not for the time being go into the transition and the turbulent zone. So all our analysis will restrict to the laminar zone. Let's come to the experimental picture, how it looks like. So this is something picture, right? So if it is a plate, if the flow is coming, it is hitting the plate. Both sides of the plate, boundary layer theory, boundary layer is forming. Now there is a natural question comes to mind: why we need to study this boundary layer, right? Is it still important that boundary layer study? Because in 1904, Prandtl might not have a supercomputer, Prandtl might not have CFD, Prandtl might not have a lot of numerical technique, but we are today in 2021. We have a SPC available with us, we have CFD package available with us, we have a robust numerical algorithm. Is it important? The answer is yes. Still, the boundary layer theory is quite relevant. It gives detailed insight into the hydrodynamic analysis. Anywhere we are doing analysis in the fluid domain, we have somewhere the fluid domain is confined within the solid surfaces. To those solid surface play a lot of important role. Just like in turbulence, the solid surface triggers sometimes the turbulence because of the roughness, solid roughness. So this viscous sublayer is formed across the solid surface. A lot of important things. So still today's date, the flow with a boundary layer flow has some importance. The flow we can assume invisible, it's very away from the solid surface, right? The viscosity or the property of the fluid, the viscous property of the fluid is somehow restricted near the solid surface. Still, even if after 120 years of the discovery, the boundary layer phenomena has a great relevance to us to analyzing to a lot of day-to-day flow and its application. Let's come. So, what are the boundary layer other things, the mathematical equation and all? Hmm. Okay, just see, this is my boundary layer over a flat plate. So boundary layer can be formed over the flat plate, can be over a core plate, can be formed over a blunt body or block body. So boundary layer can be developed across any solid surface, right? For the preliminary analysis, here we are developing the boundary layer flow over a flat plate, right? Just you can see that the uniform stream of flow is going on, and just you put a flat plate in the uniform stream, right? And how the flow is going on, right? So here you can see numerically I have computed how the boundary layer looks just from the surface of the flat plate, right? So what happens? So Navier-Stokes equation as a whole, it's a coupled partial differential equation and it's very complicated in nature. So the closed form of solution is doesn't exist, right? To simplify that, Prandtl has some assumption from where he simplified the Navier-Stokes equation to derive this boundary layer theory, right? What are those assumptions? The flow is incompressible. Here we assume the flow in a 2D plane or the 2D steady flow. There is no mode flow changing with respect to time. It's a two-dimensional steady flow, right? The boundary layer is slender, right? Slender means it's a complicated term. I'll explain what is the meaning of slender layer, right? And the boundary layer theory monotonically grows. The term slender stands for here the plate over which we are analyzing the boundary layer. It has a long length, right? What is the mathematical definition? Subsequently, we will see in the next slides. And monotonically grow means we are not going to the transition zone or the turbulence zone. We are restricting our discussion within the laminar framework in which the boundary layer is monotonically grows, right? So let's come to the governing equation, Navier-Stokes equation, right? So restricting our discussion to two-dimensional steady and flow over a flat plate thing. It's not like that Prandtl assume the flow is incompressible and 2D. It's not like that boundary layer doesn't exist for compressible flow or boundary layer doesn't exist for three-dimensional flow. Boundary layer exists for compressible flow. Boundary layer exists for three-dimensional flow. But for the sake of simplicity, Prandtl first assume the 2D and incompressible flow, which is very primitive and it's a very good thing to understand something theoretically. Let's go see the Navier-Stokes equation in the two-dimensional space, right? In this Navier-Stokes equation, I have a density, its rho, I have a viscosity, its kinematic viscosity nu, right? Normally, what will happen? The first equation represents my mass continuity equation. It is universal saying my mass is conserved for the incompressible flow, right? Because of the flow is incompressible, I have taken rho from the left side, inertia side, and divide the rho on the right hand side. So this dynamic viscosity mu by rho term give me this mu or the kinematic viscosity. Even earlier I have discussed this viscosity is a messenger. This acts like a messenger. This gives the message of presence of the solid wall by the propagation of the viscosity, right? Even if there is a single fluid dynamics, you have two kind of viscosity. Even if the physical phenomena remain unchanged, you have two notion of the viscosity. One is dynamic viscosity mu, one is the dynamic viscosity to density ratio that defines the kinematic viscosity mu. So what is the importance of having two viscosity, right? The kinematic viscosity, something gives the idea of the depth up to which the disturbance propagates of the boundary layer. Even if there is a standstill water on the surface, you generate some disturbance. How deep the disturbance will propagate, that is somehow related to the kinematic viscosity. And how it is related, we will see in the next session. And the dynamic viscosity is related to some property of the fluid that is called viscous, laminar, viscous dissipation. What is that? So whenever there is a fluid motion, by virtue of the friction between fluid, the kinetic energy sometimes dissipated in terms of the heat, and this in that case the friction occurs at the molecular level, and this dynamic viscosity represents the viscous dissipation, right? Even if they have the same physical term, but they have two representations, that because physically they represent two different phenomena. One towards the how much deep the disturbance propagated, that is the kinematic viscosity, and the viscous dissipation by the dynamic viscosity. Let's come to the x momentum equation, y momentum equation, right? These are very standard. This is my steady state Navier-Stokes equation. I have a convective terms on the left side. I have a pressure gradient term on the right side, first term, the negative del P dou P by dou X term. Okay. Then this new times, these are the diffusion term. They represent my viscous dissipation, right? To solve this set of equations, we need a set of boundary conditions, right? What are the boundary conditions? As I mentioned, in the solid surface, the solid is not allowing the flow to be penetrate along the length of the solid or tangentially pass over the solid, right? So based upon that, we have two conditions. First condition is no slip and no penetration. So at y is equal to 0, suppose I have a xy coordinate motion like this. My x axis represents the horizontal axis, y axis represents the vertical axis, right? At y is equal to 0, that is above the flat surface, flat plate surface, my u is equal to 0 and v is equal to 0. Means I have a no slip boundary condition and no penetration boundary condition. At the again, if you move away from the solid surface, what will happen? The flow gradually get disturbed by the presence of the solid, and at certain point the flow is almost uniform, right? So what will happen? Then at a point y is equal to delta. This delta is variable. With respect to x, at each point my delta has a variable. It's not a fixed kind of thing. This is here delta 1, this is some length, this is at the delta 2, this is some length, this is at delta 3, this is some distance, right? This delta is keeps on changing with respect to time, but at the point delta, means at the boundary layer edge, what is my condition? My u is equal to u infinity, means the velocity just above the boundary layer edge equals to the free stream velocity. U is equal to u infinity. My v is equal to v infinity. Means in reality there is not any v infinity kind of thing. This is just for the sake of understanding. Let's assume the v is equal to v infinity at the boundary layer edge, right? Because it's a one-dimensional flow, v equals to 0 at the core or at the far away from the flat plate, just at the boundary edge, just assume v is equal to v infinity. And what is the position of the edge? What is the good approximation? Normally, if I go on increasing from the 0 velocity to some velocity which is to u infinity, and assume a point where the velocity is almost 99% of the core velocity or the free stream velocity, that point I will assume it's my edge of the boundary layer, and I will draw a boundary layer like this. Now the challenge is to find the quantitative information like drag and skin friction, all those things from this phenomena, right, and solve the Navier-Stokes equation. It was maybe it is too simple in today's date to do the solution with this. After looking at this equation, one might be thought I can go and write every code to solve it, but those days it was not that simple. Okay, there are a lot of method of solution exists for this boundary layer method. Let's go by the primitive one, that is the scaling analysis, to derive the boundary layer equation first, right? So what is this scaling or order of magnitude analysis? In this order of magnitude analysis, we have seen a different terms in this Navier-Stokes equation. We have to find out the intensity or the strength of each term compared to other term, how what is the their order, how strength, which order of magnitude they stand compared to the other term. That is called order of magnitude analysis or the scaling analysis. This is help us to what? This helps us to simplify the problem. We can find out some simplified version of the Navier-Stokes equation that may be help us to solve the problem, right? Then in this order of or magnitude analysis, we approximated the term. That's why there is a tilde say symbol over here or big O notation over here that represents the order of magnitude thing. If we found some term is there which is mathematically relevant, physically may not be relevant because the strength is very low, then we neglect that or drop that term to make the equation simple, right? Let's come, okay, order of magnitude analysis, okay, where our x and y, they are the independent variables. They are varying x and y direction. U and v, they are dependent variables. Let's see what is the order x and y are varying, right? My x is varying over here from a position 0 to length of the plate. Maybe say if the length of the plate is L, my x is varying from 0 to length of the plate. My y is varying how much? My y is varying from 0 to length of the boundary layer delta, which is again a variable delta 1, delta 2, delta 3. So my y variance is from 0 to delta 1, right? So if I have a delta x, right? So delta x is nothing but L minus 0, that is L. If I have a delta y, that is nothing but the thickness of the boundary layer itself, delta minus 0, that is the delta, right? Delta y equal to delta. So what is the variation of u and what is the variation of the v? My u is varying somewhere from 0. Here in the free stream, u is reaching at u infinity. So what is the total variation in u? The variation is u is equal to u infinity minus 0, that is delta u equal to u infinity. The variation in the v, I assume it's a v infinity is the velocity of the boundary layer. So it's from v infinity to 0. So v infinity minus 0 equal to v infinity, right? Let's come to the scaling analysis of the mass continuity equation, right? This is my mass continuity equation. Here, each term I have to do some approximation. So delta u by delta x, right? I have to assume what is the value of delta u. The delta u value, from here I find out delta u value is nothing but my u infinity, right? Delta v value is equal to v infinity. Delta x is equal to L, delta y equal to delta, right? Small delta. Just put all those values over here, right? After putting all those values, substitution over those things over here, you will find an expression u infinity by L is same order of magnitude as v infinity by delta. This both terms need to be same order of magnitude, right? There may be opposite sign because they have to be positive and negative term. When they sum, they should be give 0. But they have of same order of magnitude. If this is 20, this has to be minus 20. If this is 50, this has to be minus 50 kind of thing. The order of magnitude is same. From the first scaling analysis, what we'll get? We'll get that hypothetical v infinity term. The v infinity term is nothing but u infinity into delta by L, right? So u infinity is my free stream velocity, which is physically defined. Delta is my boundary layer thickness. L is my length of the plate, right? Earlier, I have used a term slender, right? So what is the mathematical definition of a slender? If my plate is of very long thickness, very long thickness, L is quite high. Compared to the delta, if my L is very high, so what will happen to the ratio of delta by L? The ratio of delta by L will simply approaches to 0 because in the denominator we have a very big term. In the numerator we have a small term, so the ratio will be approaches to 0.